So first, I will go through a short product overview. The Abaqus Knee Simulator is an automated modeling tool to build advanced knee implant simulations based on well-known implant evaluation workflows. For people who are familiar with Abaqus, this is the vertical application built upon Abaqus CAE, and the simulations are based on Abaqus Explicit. The Abaqus Knee Simulator has two interface modes. First is the designer mode. Here is the design. This mode is designed for users who are not familiar with Abaqus and Abaqus CAE. In this mode, only tools that needed to build the Abaqus Knee Simulator model is collected in the interface. The second mode is the analyst mode. This mode extends the functionalities of Abaqus Knee Simulator by providing all the tools and functionalities available in Abaqus CAE. Both modes build upon the same same model database, and which ensure a streamlined interchange of models between the designer and the analyst. Switches between the two modes is easy. It's done by a single mouse button click. For both modes, the Abaqus Knee Simulator functionalities are collected in the AKS panel appeared on the left of the interface. Within the AKS panel, there are two tabs. First is the Knee Parts tab. In this part, the knee implant components are imported into the Abaqus Knee Simulator. These components are mapped automatically upon import. And specifically, for the insert polymer parts, to ensure accurate contact pressure calculation, we provide a semi-automated hexahedral mesh for the contact area. The second tab is the Test Suite tab. Here is where the implant components that are imported into Abaqus Knee Simulator are selected to be included in implant evaluation workflows. Once the test suite have been created, all the models for the workflow selected are created automatically. And all the user input requested for the specific workflow are collected under one place. That include the output request, user specified simulation option. The user can then submit the simulation and visualize the results within the knee simulator. What the designer will not see in the background is that these models are finalized once the workflow models are submitted. And each of these models include a large number of features that include sections, section assignments, output requests, steps, and a large number of constraints and connectors. Next, we will talk about the workflows in depth about inside Abaqus Knee Simulator. The Knee Simulator includes 5 workflows. They are the contact mechanics workflow, simple implant constraint workflow, the tibial femoral constraint workflow, wear simulator, and the basic total knee replacement loading workflow. The contact mechanics for workflow is the analysis of basic contact pressure and area distribution between the femoral and tibial components during a simple knee flexion. Here, I want to highlight that only the knee implant components are included in this workflow. And also, there are functionalities that is common across all different workflows. First is the insert tab. Insert type. So we offer the insert to be modeled as both deformable and rigid body. The reason for providing this option is to have the option to give the user the functionality to be able to run the simulation quickly as rigid body for a quick evaluation, while when they need to have produce accurate contact pressure, they can run the simulation as deformable. Here is a comparison of the simulation time for each option. So when the simulations run as rigid for this specific workflow, it took about 30 minutes for Abaqus Explicit to complete the analysis. While when we model the insert as deformable, it's taking much smaller increment to guarantee an accurate and stable solution. So it takes 24 CPUs about 4 hours to complete the same analysis as deformable body. Another common option is the platform type. This is referring to the insert on the tibial components. So the platform can be either fixed or rotating, depending on the design you are trying to evaluate. During the analysis, a compressive load is applied on the femur component, and the value can be either a constant value throughout the analysis step, or they can be varied using an amplitude curve. The distribution of the load between the medial and lateral side can be specified by the user using the slider bar. During the analysis, the femur component is flexed to a certain flexion angle specified by the user. Here is where the user specifies how much flexion should the femur component go through. The first value is the beginning flexion angle, and the last value is the end flexion angle. The number in the middle is the increment that the Abaqus knee simulator will provide output to the user. So in this case, the femur component will start from 0 degree flexion, goes to 120 degree flexion, and the user will be able to visualize the results at 30, 60, 90, and 120 degree flexion. As the compressive load is applied on the femur component, the other degrees of freedom for the femur component can be either left free or be fixed. Once the user is satisfied with their simulation options and output requests, they can then write the input file and submit the simulation. And the simulation can run either in the background or be submitted to a HPC queue using either single or multiple processors. For the contact mechanics workflow, the cost for running a single physical testing is around $14,000, and it takes about 4 weeks. The cost doesn't really include the cost for constructing the prototype and all the manpower needed for that. It's just for the physical testing itself. While running the evaluation using Abaqus knee simulator, the user only needs about 10 minutes to set up the model, and the simulation runs within 3 hours. This is done using the value we report here for analysis that's done using 24 CPUs. The second workflow is the implant constraint workflow. This workflow is the analysis of laxity between the femoral and tibial components in the absence of any soft tissue structures. As compared to the previous workflow, one additional component that is included in the analysis is the tibial tree component. This is not required to be imported by the user. Instead, it's provided by the Abaqus knee simulator for output purposes. Here, I like to point out, although the name is the same for input, the flexion angle in this case not only indicates the beginning and end angle and the output angle, it also indicates where the laxity test will be performed. In this case, since I entered a 120 degree interval, the laxity test will be done at 0 degree flexion and 120 degree flexion. So if a smaller increment is provided by the user, that means a lot more laxity tests will be performed at each interval. A number of laxity tests are provided for this workflow that include the anterior-posterior displacement laxity test, the internal-external rotation test, the medial lateral displacement test, and for each laxity test, the load is applied as a boundary condition instead of a loading condition. For this workflow, the cost for performing a single laxity test is around $7,500 and takes roughly 4 weeks to perform one single test. Well, as you can see, compared with the physical testing, running simulations saves a lot of time and also cost. The third workflow is the tibial femoral constraint workflow. This is the analysis of the laxity, just like the previous workflow. However, in this workflow, the tibial femoral joint with soft tissue representations are included. That include ligaments and bones around the knee joint. And the user can selectively cut ligaments to represent surgical removal of these soft tissues or clinical weakening of some of these soft tissues. Similar to previous workflow, a number of laxity tests are included in workflow 3, and they are the anterior-posterior load, internal-external torque, and valgus-varus torque. As you can see here, the load are applied directly instead of displacement. Provided along with all the ligaments is control over the ligament properties. Ligaments are pre-strings in all these simulations. The user can control the amount of pre-string, and the user can also scale the linear stiffness of these ligaments. Although they are non-linear, but we provided the scaling for the linear stiffness portion. The bone components in this workflow can be shifted. For this specific workflow, because there is cadaver knee joint required for the physical testing, it's hard to come up with the estimation on the cost for physical testing. But what we can say is that these physical testings are so cost and the time prohibitive, it's not really a tool being used as earlier stage evaluation of knee implants. Instead, they could be used as final evaluation on implant designs. So by providing these more complex workflows with Abaqus Knee Simulator, we allowed access of these advanced simulations as earlier stage evaluation tool for implant design. The fourth workflow is the wear simulator. It is used to predict wear on the tibial insert over a number of gait cycles. We provide equivalent parameters as in the actual physical wear tester that include the gap distance and the linear stiffness. Two wear algorithms are provided for this workflow that include the more established Archer's Law wear algorithm, which is the isotropic wear. We also provide the latest research results, which is the cross-shear wear algorithm. Here, the change of direction for between the femur and the components in terms of contact slip accelerates the wear between the femur and the tibial components. For the wear simulator, because it requires a large number of cycles to be simulated in the physical testing, the cost runs up to $100,000 to run a single test. And more importantly, it takes a very long time for the wear simulator to complete one round of testing. By running simulations, these analysis can be done in a very reasonable amount of time. Finally is the last workflow in Abaqus Knee Simulator. This is the most complex workflow. It is the basic total knee replacement loading workflow. This is the analysis of whole joint mechanics during activities of daily living under basic muscle-loaded conditions. Compared with the tibiofemoral constraint workflow, additional muscle and bone and the soft tissues are included. A number of daily activities are provided as built-in loading conditions that include the gait loading condition, chair rise, deep squat, and step-down loading conditions. Provided with the muscle property is again the ability for the user to change the pre-strain and the linear stiffness of the muscle. Again, for the basic total knee replacement loading workflow, because of a whole joint is required for the physical testing, the time and the cost for running these tests is very prohibitive for design evaluations. So now I will pass along to Dr. Rockhatter for a review on the research validations for these workflows.
Good morning or afternoon, everybody. Just wanted to say a few words about some of the model validation work that's been happening in the literature and how some of those are related to the computational framework that we've provided here. Next slide, Cheryl. Great, thanks. Obviously, for everybody here, model validation is key to our overall success, both for our developers as well as for the end users. There's a host of current literature that shows explicit FE model validation for these types of analyses, and they all include predictions of contact mechanics, which requires, of course, specific material models and contact algorithms within Abaqus. The contact mechanics work has been well validated in the literature, both for orthopedics as well as a host of other industries, really. So I kind of wanted to concentrate on these second two to talk about actually prediction of tibiofemoral and patellofemoral kinematics under known dynamic loading conditions, as well as wear performance, as these are the two probably that we're most interested in at this point. Go ahead with the slide, Cheryl. Thanks. So I thought I'd highlight a few publications that are quite relevant. This one is from Knight in Journal of Biomechanics. It is a simulation of the Stanmore knee wear simulator. You can see the schematic on the left. Just has the implant components. There's a compressive load, a flexion angle, an IE torque, and an AP force. And you can see also the springs, anterior and posterior springs that are representative of the physical constraint in the knee simulator. So it's a forward dynamic or a force-controlled simulation, and you measure the IE rotation and the AP displacement resulting. So I just wanted to point out here from one of the figures in the paper that they've been able to do a reasonable job in predicting relative AP and IE kinematics when compared to the experiment. In addition to the kinematic performance evaluation, they're also looking at the ability to predict wear. In this case, this particular paper is just using the Archard's law. But it shows that, at least from this qualitative comparison that we're looking at here, that the wear scar for these two implant components was well represented, both in terms of the locations as well as in sort of the relative depths of wear on the medial and lateral components. And that's also quantitatively shown here, just in terms of wear volume or really weight loss compared to 2 stations of the experimental simulator. So I wanted to highlight this paper because it's just tibiofemoral, but it shows prediction of both kinematics as well as relative wear simultaneously. So there's a host of other literature that is out there that shows kinematic validation also, some for just tibiofemoral, some for both tibiofemoral and patellofemoral simultaneously, coming from a few different groups. Next slide, please. I thought I'd highlight just a couple of these. This is from a Canadian group. It basically shows an explicit finite element model of a knee simulator rig, sort of a more lower limb type rig. And this took the next step to predict simultaneously both kinematics for the patellofemoral joint as well as the tibiofemoral joint. And you can see on the right some comparisons of kinematic predictions with the experimental cadaveric measurements, and you can see reasonable model validation there. And from my group here in Denver, there is a recent publication comparing some of our whole joint knee kinematic predictions with those produced experimentally in a wear simulator. So you see in each of these different flexion angle figures the experimental simulator representation as well as the relative positions. And next slide, thank you. And we've basically shown that you can do a very effective job of predicting both tibiofemoral and patellofemoral kinematics with this known, well-controlled dynamic loading condition. So I just wanted to show a few of these so that people are aware of the type of literature that's out there currently and the type of validation associated with these types of models. We obviously have a commitment to ongoing model validation whenever, wherever, really it's available through, hopefully through collaborative work with some customers and available experimental data.
Thank you, Paul. So now, before we start the actual product demonstration, I just want to go through the step-by-step on using Abaqus Knee Simulator to set up these advanced knee implant evaluation workflows. First, the user import knee implant components, then create test suite, which is a repository of workflows. Next, we provided tools for the user to check for interference. The reason for doing that is because the analysis was executed using Abaqus Explicit. Abaqus Explicit may run into issues if there are initial interference between the components. So we'll provide that tool to check for interference and highlight any surfaces that are having interference. Then the user are given the tools to adjust instant positioning if necessary. Then the user go through the workflow definition that include define output requests, set the simulation options, run the simulation and monitor its progress, then visualize the results. So next is the demonstration of Abaqus Knee Simulator. We had issues running the live demonstration along through WebEx. So instead of showing it live, we will be showing a video of the demonstration, and I will talk through the demonstration. Abaqus Knee Simulator always starts from the designer view, designer mode, and the user have the option to either create a new database or open an existing database. In this case, because I need to show the visualization of the analysis results, so I selected to choose opening an existing database. So once the database is opened, the user can look at the interface mode of the Abaqus Knee Simulator. So go through the Knee Parts tab and the Test Suite tab, which is a repository of either implant components or Test Suite. To import a femur component, I just click on the femurs. There are different sources supported by Abaqus Knee Simulator that include the neutral file, CAE model, or CAD interfaces. In this case, we chose the neutral file. And the user can select to choose either a left or right knee component. So all the anatomies inside built-in Abaqus knee simulator belong to a right knee. So in the case of a left knee being imported, the implant component will be just mirrored to represent a right knee component. A number of neutral files supported. The user can give a description of the components imported. Next, the knee simulator asks for a few landmarks on the implant components. So for each implant during import, different landmarks are requested. So these landmarks are needed for both meshing the components and also aligning the components in the assembly. First is the plane on the femur components. Next, we ask for the 2 dwell points on the femur components. I know that different companies may refer to these landmarks using different names. So what the dwell points in reality are the lowest point on the femur components when it's in its designed vertical location. So if we drop a ball on that surface, the 2 points should be the location where the balls will settle eventually. The user can either pick this point from the screen or they can enter the coordinates. So now the femur component has been imported, and you can see the mesh is generated automatically. Next, we import a tibia component. Again, different files and different landmarks are provided. So the user needs to pick a plane that's parallel to transverse plane. Here, instead of picking the points from the screen, we enter the coordinates of the 2 dwell points and the tibia component just to show different options. Next, the GUI asks for whether the user would like to continue with the geometry and meshing operations. The reason we provided this option is just in case you are importing a part that has been already meshed. In that case, you can skip this step. So here, this is the semi-automated tool we provide to generate the hexahedral mesh for the contact area. The first thing that you'll be prompted for is the axis that's representing the global knee axis. In this case, which should be the z-axis. So this will be the axis we use to generate the ellipses used for the positioning. Now you can see the ellipses are generated, and we provide the tools to control the minor and major axes of these ellipses. And the idea is to have the ellipses as big as possible to cover all potential contact area, and again, but at the same time to avoid any interference with the external edges of the implant. Next is partition and mesh. A mixed mesh will be generated automatically with hexahedral mesh in the contact area and the tetrahedral mesh for the rest. Next, we import the patella button components. Again, one planar landmark is required, and the 2 landmark points on the patella button, one on the medial edge and one on the curved surface. Again, the user can either mesh it in Abaqus knee simulator or just skip this for a part has already been meshed. So once the implant parts have been imported successfully, they will have a green check mark next to them in the knee part tree. The user can choose to edit the surface and landmark points if they happen to pick the wrong surface or the wrong points. And they can also swap the dwell points if they mistakenly enter the lateral side for the medial side. They can do it here. And also, they can create sets and surfaces for output here. So if the user chooses to create sets and surface in the knee parts tab, those sets and surfaces are automatically generated for all the workflows. Later on, you will find that in each workflow, the user can also create surface or sets, but in that case, all the surface and sets will be available only for that workflow. Here we use the tools available in Abaqus CAE to pick surfaces by angle. And now we switch to the analyst view just to show how the other functionalities in Abaqus CAE can be used in combination with Abaqus Knee Simulator. So once the knee parts have been imported into Abaqus Knee Simulator, they will all appear under the knee sim-parts model. So this is, like I mentioned, this is back in the analyst view. As soon as the user changes to another module inside the analyst view, they will have access to the model tree. So again, in the knee sim-parts model is where all the parts and material reside. You can see the parts I have just imported, all the surfaces and sets created. Abaqus Knee Simulator provides a few material models as built-in materials, but the user can always create their own materials based on material test data. And this is a demonstration on how to do that, on how those materials can be used by Abaqus Knee Simulator. In this case, we will create a Drucker-Proger plasticity model, which has been used a lot in modeling the polymer insert. So the built-in model is a simple elastic material. So now we create a Drucker-Proger model. As I mentioned, since Abaqus Knee Simulator uses Abaqus Explicit as a solver, we require the user to provide the mass density for each material. Enter the elastic property. Here, I just want to mention that Abaqus Knee Simulator, because it has the built-in geometry and the materials for the soft tissues, we do have a built-in unit system. It is the Isight units, so the force will be in Newton, the pressure and modulus will be megapascal, and the length unit will be millimeter. Drucker-Proger plasticity. Also, because the simulator uses Abaqus Explicit solver, we recommend the user to enter a damping, especially alpha damping, for each material they define. And what we found is that 100 alpha damping is a reasonable number to use for most polymer material. This is to remove any noises in the solution. Now we go back to the knee simulator designer mode by first going back to the knee simulator module and then click on the designer icon. Now we're back to the beginning of the demonstration where the interface mode is. Next, we demonstrate how a test suite can be created. Simple click on Add Test Suite, gave this test suite a name. So the existing test suites were created by one of our interns, and she arranged things by workflows. So she had only one workflow for each test suite she created, but you can do it in any way you like. So you can either arrange by workflow or you just arrange by design. So here you can see the material model we just created in the analyst mode has been populated in the drop-down menu and can be selected for the implant parts. So this is one way we envision how the analysts work with the designers. The analysts will create these advanced nonlinear, could be viscoelastic material models for the polymer, while the designer just pick whatever the material the analysts recommend them to use. And the user can select which workflows to be included. So for the tibial-femur constraint workflow, because we have representation of the soft tissue, the user can select to either represent the soft tissue as 1D element or 2D element. Similarly, for the basic total knee replacement loading workflow, they can choose the modeling space for the ligaments, and also for the quadriceps, they can model them either as a single bundle or multiple bundle. And in this case, we chose the simplest option so that the models will be generated in a reasonable amount of time. So this is the real time. I didn't speed up anything. You see how quickly these models are generated, and the implants are assembled and positioned in the assembly along with all the soft tissue and hard tissue provided for each workflow. And at the bottom, you see all the features have been generated for each workflow. Now we have the workflow generated. The user can go ahead and review each workflow. Tibial-femoral constraint, wear simulator, total knee replacement. All the workflow models have been generated. And next, by right-click on the workflow, the user can access the interference check. Now, because there are interference between the two components I imported, they are highlighted. Next, I go back to the test suite, right-click on the parts, and I have the tools to move these parts around. So in this case, I just translated the femur components along the Z direction by 1 millimeter. And now I went back and checked for interference again to make sure that the interference has indeed been removed. Now I don't see any interference, so I can go ahead with the simulation options. So now to demonstrate, each workflow has different output requests and simulation options, but the general concept is quite similar, so we decided to demonstrate the most complex workflow for this webinar. So basic total knee replacement workflow output request. A common option for all different workflows is where the output needs to be provided. So for sets, the user can select the previously defined sets. If they haven't defined these sets, they can create these sets by clicking on this little icon on the right. And also, they can create surfaces on the fly. As I mentioned, these surfaces and sets are only available for the specific workflow where they created. While for these sets and surfaces created at the need parts level, they will be accessible for all workflows. There are various output variables provided for each workflow. For more complex workflow, there will be both muscle output, ligament output, and contact output. While for more the simpler workflows, there will be mostly contact outputs and force constraint type of output instead. And for some outputs, there are options to choose output to different sets and surfaces. Under simulation options, common options include deformable or rigid insert, deformable rigid button, and the user can choose to have the rotating platform and pick the center of rotation. The user can select which ligaments to be cut, and they can use the control button to select multiple ones, or the shift button to select a number of them. A number of tests included. For each of these tests, the load are applied as default, and the user can choose to plot these built-in loading conditions, and you can see how different they are from one loading condition to another. And they can also edit these load data using their own either kinematic study or test measurement data needed for this specific activity. Next, we demonstrate the visualization part of these workflows. So we use an existing workflow that has been executed by one of our interns here, and she has picked specific simulation options output requests for me, and when we click on result options, the ODB will be populated. The user can choose which results they would like to see in which area to be plotted against time of flexion, and they can choose whether they want to plot the XY plot. In the case of XY plot, they can also choose to report the XY plot to a text file. They can also create a contour plot for specific output. In this case, it's the contact pressure. And they can visualize the progression of contact pressure or any contour outputs over time using the animation button. They can control which components are being showed. In this case, we have all the components viewed in the viewer, and play the animation again to see how the flexion is executed during the analysis. And another tool is a special tool we created for knee simulator. Is called plot the trajectory. So the user can pick any point, any moving point on the implant components or on any ligaments or bone parts. They can pick any points here, and the knee simulator will plot the trajectory of this point during the analysis. So in this case, I picked a point close to the dwell point on the femur components, and the Abaqus knee simulator plotted out how this node moved over the flexion range specified. And this trajectory plot can be used to study how and quantify how the components have been moving at a specific point where the point have been. And they can look at different views of the trajectory. And they can also delete this trajectory from visualization. Next, we move on to the visualization of the basic total knee replacement workflow. In this case, there are more output variables available for different loading conditions. In this case, I choose the muscle output, plot the force over the gait cycle, and I pick the patella ligaments. Then the outputs over time, over the gait cycle for this specific ligament is plotted. You can also visualize contour plots of, for example, cumulated contact patch. This output again is created specific for the knee simulator. Instead of contact pressure for one single frame, this is the summation of contact pressure over the entire loading cycle. The reason for providing this output is to give a visual on where the points have been participating in contact, and which indicates where the wear on the polymer part will be. and the user can go back to the analyst view to have access to more visualization tools. In this case, I showed how different steps and output variables can be selected to be plotted. Instead of the contact output, I choose the stress output for the components and how it's progressed over the gate cycle. And we can see how it's being developed, the stress is being developed on the insert. And as I saw this result for the first time, I noticed that there was some lifting at the end of the gate cycle on the medial side. As you see here, the medial side no longer has any stress at the end of simulation. So I suspect there was some simulation options that triggered this behavior. So I look at the assembly of the models, and to visualize, since in this case the ligaments and tendons are mostly represented as 1D, so I have to visualize the connector to be able to show where the ligaments and tendons are. So to access that, I went to the view options, ODB options, and by turn on the displays of all the connectors, which is the elements used for modeling these ligaments and tendons. So as you can see, the MCL is not really in the model. So I suspect the intern has cut that ligament. So to check that, it's really easy. I just went back to the knee simulator in this case, and I could choose to go back to designer view. Actually, I could stay in analyst view. I could still check what the simulation options she has used. In this case, indeed, she has turned off the MCL from the model. So that concludes the demonstration.